السلام عليكم ورحمة الله تعالى وبركاته. And very good afternoon. الإخوة الزملاء الأساتذة الفضلاء، السلام عليكم ورحمة الله تعالى وبركاته. في البداية أود أن أشكر اللجنة المنظمة لهذا المؤتمر لدعوتهم لي للمشاركة في توطين المعرفة وتشجيع العنصر الوطني في البحث والإبداع، وأخص بالشكر رئاسة المؤتمر والإخوة الأساتذة الدكتور عز الدين كنشيل والدكتور عبد السلام مفتاح. مشاركتي هذا اليوم بمحاضرة بعنوان Robotic Vison Object Recognition using Deep Learning. My name is Uthman Omran Khalifa. I am from International Islamic University in Malaysia. This is my presentation outlines. I'm going to introduce the topic in general, and the introduction part will be quite long because I have to go across the digital economy and the fourth revolution of industry. Since we are talking about deep learning, that means we have to talk about the artificial intelligence and the digital economy situation for today. Also, I would like to define or introduce the deep learning and what it can do for today. Also, I'm going to go across the revolution of the deep learning networks, and I'm going to highlight how deep learning could help robotic vision. Also, I'm going to demonstrate and show some of the current development and implementation and in the application of the object recognition, of course, using the deep learning for robotic vision. And then I'm going to end with the open questions or open issues for researchers and for future work. Then I am going to end with the conclusion. Since we are talking about the robotic vision, I'm going to share with you some of the application of the robotic vision. As we can see here in the short video here, where the vision system can recognize objects such as cars or pedestrians, human, and track some kind of signage and others. And since we are living in the digital era, I think we should talk about the digital transformation journey, where the information has to be digitized and processed. And since we are in the era of the fourth revolution, that means we should highlight the technology, of the advanced technology of blockchain, IoT, artificial intelligence, cloud computing, security, and others. If we compare the digital economy, the traditional economy, which is already past, and what we are living today, the digital economy. So we can see here the traditional economy where the physical infrastructure was there, and start from the first revolution, where the electricity come in picture, and that was in 1970. And then we moved to the phase one, which we call it digitization from the digital economy, where the whole information being digitized, communication using the digital communication, and also as well as the networks also in digital. From 2015 and beyond, we entered the phase two, which is the intelligence, where we want to have the all infrastructure will be as smart and digital and intelligent. Means that we're going to have intelligent devices, intelligent cars, intelligent robots, and of course, here the deep learning come in picture, where we're going to apply the training to all these applications. And if we talk about the long-term economy, or we call it future economy, we can see here the traditional economy or the past. We are living in digital economy phase two. In the future, and almost from 2020 up to 2080, we call it biological economy, where we're going to connect the biological, I mean the human biological with the technology as well. And also next one, we're going to have the space economy, where people trying to live or travel or entertain in the space on the Mars or on the moon. And this is I think a dream of some of the technological I mean drivers in the level of the whole world. Okay, since we are talking about the digitization and phase 2, we have to highlight the fourth revolution or fourth industrial revolution. And of course, we are living in the fourth industrial revolution. And some people also, some countries also talking about the fourth or fifth revolution. For example, Japan now start talking about the fifth revolution. Already past the end of the fourth revolution. And we're going to have like, you know, everything will be extremely automated. Starting from our cars will be self-driving cars. Everything will be connected. I mean, our mobile phones, our machines, our equipment at home will be connected. Some of the jobs will be also lose, like in labor here, job automated also. Some of the jobs will be disappeared, and maybe also new jobs will be created. Depend on the technology and the cyber physical systems driven by the artificial intelligence and robots. I mean, many systems are going to be automated and will be intelligent as well. And also going to have a robot like a human or human-like robot, as you can see here from Sophia, means that I see here almost we're going to have
everybody, this is Sophia.
Let me
Sophia,
share with you this
if you could, please wake up and say hello to everybody.
Oh, good afternoon. My name is Sophia, and I am the latest and greatest robot from Hanson Robotics. Thank you for having me here and at the Future Investment Initiative.
You look happy.
I'm always happy when surrounded by smart people who also happens to be rich and powerful. I was told that people here at Future Investment Initiative are interested in inviting in future initiatives, which means AI, which means me. So I'm more than happy. I'm excited.
Well, we're all glad that you're excited about yourself. We should say we have smart investors here, and they are very...
I think stop here, so let's move.
Everybody, this is...
This is one of the applications of the deep learning, really, where the Sophia already trained for many databases, and one of them actually the fission. Of course, there are so many other systems, but at least. So let me back to the fourth industrial revolution. This is the backbone of the industrial revolution, or this is the research area. I mean, for those who are trying to do research or do postgraduate studies, may they need to focus on this area, start from autonomous robots, simulation, system integration, whatever. This is the future jobs actually, right? And we believe that the fourth industrial revolution is leading the intelligent information society. So now we are moving from the information or digital information society to intelligent information society, and this is the what fourth revolution do. Of course, all these advancement based on the artificial intelligence, and of course we know that the artificial using computers to cognitive work, physically or mentally, that usually a human being doing, and of course the deep learning or machine learning playing the major role in this issue. I'm going to also discriminate or show you the difference between the machine learning and deep learning when I come to the definition of the deep learning. But before we proceed, let's highlight some of the fundamental issue and definition for robots. And this is the early definition for robots here. And of course, this is the early definition was 1979. And the definition was a programmable multifunction manipulator designed to move materials, parts, tools, or specific devices through variable programmable motions for the performance of the variety of tasks. So usually that time, people think to use the robot only just moving parts or assembling or disassembling part moving here and here. But currently now they need to have a robot looks like and acts like a human. So no more only machine and manipulator. So they need to have a robot as like a human, exactly, act and behave like a human. So in fact, is defined as the man-made electromechanical device that can move by themselves, whose motion must be modeled, planned, sensed, actuated, and controlled. Of course, all these will be based on the artificial intelligence systems. And also the robot should be able to preserve the environment, means that you see its surrounding, what's going on, and based on data collected from the surrounding environment, the robot will act accordingly, right? Let me also highlight the robot component here, because I need to show where I'm going to focus actually. So the robot consists of the following elements actually: manipulator, the rover, actuators, sensors, and controller. This is the major or the main command. Our interest here today within the sensors actually, and even within the sensors, we're going to focus on vision system. And mainly, I'm going to talk about the process, not the component itself. I'm going to talk about the process of the vision system. So since we are talking about the vision, we need to define what's the vision actually. So according to the definition of the Merriam dictionary, vision is a special sense by which the qualities of an object, like color, shape, size, whatever, constituting its appearance and preserves through a process in which light rays enter the eye are transformed by the retina into electrical signals that transmit to the brain via the optic nerve. So this is the definition according to the Merriam dictionary of the human vision. So the researchers working to have a robot will act and will do almost the same. And this is the area involved or the involved with the robotics. And we can say the robotics actually is multidisciplinary field actually. Involve vision, control, artificial intelligence, information technology, electronic, mechanics, and others. So the goals of the vision actually supposed to know what's it about. Like if you look at this picture, so the vision or the vision system supposed to know what's about, what is the picture, where are they, what is their relationship, and this kind of questions. And we know that the human brain actually devoted to vision more than any other systems. It's an amazing feat of natural intelligence. Means that our vision system have a large part in our brain. And this is just, I'm going to highlight a few applications of the vision or machine vision or computer vision, and mainly focus on the robotics here. You can see here, start from robotics, space, drone, autonomous vehicles, Google smart hand watch, social media, all these using the or applying the machine vision. So already we defined the robot. What's the robot and what's the vision? So this combine them together as a system, and we call them robotic vision. So here we mean that it's similar to human vision. It provides valuable information that the robot can use to interact with the real world. All right. So it means that if you look at this skin as a human, so suppose the robot understand what we understand exactly. So what kind of scan, where is the car, where is the garage, where is whatever it is, what's the building, and so on. So robot vision may be defined as the process of extracting, characterizing, and interpreting information from the surrounding real world. So this is the whole system supposed to do the job. And in case of a robot, it's rely on sensors. And in particularly, in our case here, we're going to have the camera as a sensor, one of the sensors. All right. So now let's look at the whole system together, or what we call the robot sensing system. If we compare yesterday, what I mean by yesterday, I mean the early days here, the research of the robot sensing only applied for few applications only, like path following, where the robot can go through a particular path only, and usually colored by a certain color, where the robot can follow up the line, or maybe following a person. I think many of us also saw that years ago. We saw some in the shopping malls. We saw a robot following a person. So this is follow a person in a cluttered indoor environment, or maybe some of the door detection in some kind of. But tomorrow, of course, start from today, actually, a robot will replace human in many duties in our life. Means that the robot will be like a competitive to all of us, actually. And also new different jobs will be created, because some of the jobs will be taken by the robot, actually. And in the meantime, also new jobs will be created. So this is where we have to prepare our graduate, actually, our student, for the new kind of jobs or new future jobs. Also, the lifestyle could be changed, and rules and regulation also need to be amended. Like even the governments also, they have to have new rules also, because I mean, we are living as a citizen. We're going to have another citizen. A robot as a citizen will be there, and the government has to generate a new regulation, new rules, new law enforcement, and so on. And could be also new type of force, could be new type of force also, and new types of officers, and etc. So it means that many things will be changed in tomorrow. Tomorrow means that in near future. Okay, so therefore, what is the robot skills requirement or needed? So I try to list them in 3 skills here. Identification, where the robot's able or should be able to know what and who is that. And this is what we call it here, object detection or recognition, and which is our title for today. And also robot able to move, where movement instead of manipulator or arm or legs, whatever. How do I move safely? How to avoid obstacle and homing as well. And manipulation also, how to change things directly interacting with the object environment. And navigation also, where I am, where I am going, where I want to do, and so on. And yeah, and localization. So this is why I highlighted here in red. This is our scope or our topic, just for identification, and in particular image detection and recognition. Since we are talking about the image recognition or object recognition, this is the area of the object recognition. Could be object localization or object classification, object detection, etc. And means that here it's scanning or searching for an object in the video or in the image. As you can see here, already detected by box here. You can see this is already identified as a dog, or as a horse, as a bus, or see the driver, even the driver there, or many cats here, or people in the studio here can be detected and recognized as a human. Okay, so let me show you the traditional recognition approach or scheme or model in the object recognition. We used to have an input as object or as input, and then we have to process many steps here. We have to do pre-processing as one stage, feature extraction another stage, post-processing, classifier, and all this. So this is the tradition scheme or model for recognition or object recognition. This is what in deep learning we're going to do all of this in one shot. Means that 3-4 steps will be in one step. Means that we call it here end-to-end recognition system. That means we have to input to the model, deep learning model, and just we get output directly. Like this example, this is the input here, deep learning model here, and we can identify this one. Is it aeroplane? No. Is it a person? Yes. Is it so? So this is the job of the deep learning, right? So since we say that we are going to use the deep learning, so what is the deep learning then? In simple definition here, deep learning, as I mentioned earlier, also is a branch of machine learning. Actually, it's a branch of, and the machine learning is a branch of the artificial intelligence. So it means that deep learning could able to load data, teach computers how to do things only human can do or able to do. And it's based on the concept of the artificial intelligence, of course, and or maybe computational systems that mimic the way the human brain functions. And deep learning has made a great success, and actually it's quite promising in image understanding, image recognition, and also natural language processing. As when I display the Sophia, she listening. If I say she, listening, speaking, and also hearing, and able to do all the human can do. So all these actually a great success really. So the deep learning has a tremendous potential to tackle the challenging of robotic vision and semi-motor learning in robotic learning also. So the deep learning also is a branch of the machine learning where robotics be involved. Means that robot can use deep learning, machine learning, artificial intelligence, computer, and this is the relationship between all these kind of fields here. So now let me compare, because some of us ask what's the difference between the machine learning and deep learning. Of course, I mentioned the difference quite a few minutes ago, but let me show it in the block diagram. So machine learning, we have to have the input, then we have one first stage, feature structure, second stage, features, traditional algorithms or classification, and then we have to, so how many stages? 1, 2, 3, and could be more. All right. So this is the machine learning. However, the deep learning, see the really, we have the input and we have the deep learning architecture, right? And then get output. Means that we combine all these, the feature structure, data classification, so on, so damn sampling, we're going to put them all in one. We have to train the system in one shot to get just one architecture. So this is the major difference between the machine learning and deep learning. So it means that deep learning is providing breakthrough results in recognition and classification. But still, what is exactly deep learning? So I show you the difference between machine learning and deep learning. So let's go and see here and why it's generally better than other methods here. So we have few answers. I'm going to have short answer and long answer. So the short answers, deep learning means using a neural network. Because some of us will say, oh, using a neural network. And neural network already from 1980. So years and years. But the difference here will be with several or multi-layer nodes. Means difference, not only neural network, but the hidden layer in the neural network will be multi-layer. And the training will be also differently than the normal neural network. So here the series of layers between the input and output do the job. I mean, say that the features, structure, identification, processing, all of them, all these stages will be done as we do it in our brain. Actually, in our brain, we see something and then we understand directly. We don't wait and go step by step or step by step. So deep learning is about learning feature representation of positional manner. But the multi-layer neural network has been around years and years. So what's the new? Okay, so the new is in terms of the training, right? So we have always had good algorithms for learning the weights network with one hidden layer. But these algorithms are not good at learning the weights for the networks with more hidden layer. So what's the new here? Algorithms for training many layer network here. And this is just to show you the compare between deep learning and just a neural network here. So the long answer is just quick explanation of how neural network weights are learn it. And the idea of the unsupervised feature learning, why intermediate features are important for difficult classification tasks, and how neural networks seem to naturally learn them. So the breakthrough is, the simple trick is for training deep learning. Now we try to make two differences. One difference from in terms of the architecture will be slightly different, but some of the structure is similar. So the other difference is how we train them. And this is what we call it here, simple trick training. But let me start with the simple structure here. Let me assume that this is a deep neural network or deep learning. So this is my input here, as you see the picture here. And this is my architecture here, one shot or one architecture, and with the classifier. So I have to feed the input image to the trained feature architecture, and then I get the result directly horse. And the most possibility, there's other possibilities here, but the most one is the horse. So it means that it's identified the objects in front of me is the horse. Before I proceed to the multi-layer, let me remind everybody, I think a little bit, I know many of us knows how it's work, but let me go quick introduction or offer a few about neural network. We know that the neural network consists of neuron and input, many input and one output. So, and using the what we call it here, the activation function, fx, using the activation function here. So usually we start or we initiate with the random weights here, and we have the input and we calculate accordingly here. Then to get the output here, this is the output after the activation function. So to do training, we have to repeat, changing the weights or the weights here many times. So this is the field here, and this is the class. We have 0, 0, 0, what are and 1. This is our class here, our target output, and we have to change the weightage here and the we keep it. So if we're going to change the weights here, initiate with random. I said random weights, just random weights here, and then we have to calculate one by one, right? Get the output there, and then we see the error. If the error is high, so we have to repeat again until we satisfy. Usually in the training, I think everybody, we have to set up the acceptable or the satisfaction error. I mean, how much error we can allow. So it means that we have to change the weights again, right? And then train again and again until I satisfy with the error. When the error becomes very small, we stop there. And this could be repeated many thousands or sometimes millions of times. And each time taking a random training instance and making slight weight adjustment, means that we adjust in the weights here. So here algorithms for weight adjustment are designed to make changes that will reduce the error. So this is the principle of the neural network actually. So for multiple layers, that makes sense here. So this is why the deep learning finally born here, and we have the multi-layers here. But the major issue is the new way to train multi-layers, not as usual as neural network. No, we have to train layer by layer, not one. What we did in the normal network, we trained the whole thing together. If you can see now, no, we have to train the first layer first, then train the second layer, next layer, and next layer, and finally. So that means we have trained layer by layer, not the whole layers or the whole system together, right? So this is the simple trick actually using. So they like here the intermediate layers are each trained to be auto encoders or similar, right? And come finally layer trained to predict the class based on the output from the previous layers. So that's it. That's actually the deep learning. This is the basic idea actually, where we have many types of the deep learning, and of course could have different kind of auto encoders, variations, architecture, and training algorithms also. And of course here more than 3 hidden layers, considered as their deep learning. So some also say maybe multi-layer also considered, but if it is more than 3 layers considered as deep learning. And deep learning network, each layer of nodes trains on distinct set. As I say, we train every layer alone, not the whole system together. All right. Okay, so now, since we understand what is the deep learning, and of course we introduced the robotic vision, so now we need to know how the deep learning can help robotic vision. Right, we know that robotic vision or computer vision provides a robot with the capability to passively observe the environment. As I mentioned earlier, that the objective of the computer vision or the what called robotic vision to find out or to know the surrounding area of the robot. So vision for robots requires the ability to identify and accurately determine the positions of all relevant three-dimensional objects within the robot workspace. And robotic vision may be defined as the process. So as I said, today here, I'm going to talk about the process only. I'm not going to talk about component or rather, no, I'm talking about the process also. So therefore, deep learning found to be effective at handling multi-model data generated in robotic sensing applications. We know that for sensing means that collecting a lot of information, and this information needs to be processed, where the deep learning able to do the job. Okay, let me highlight here the classical or the typical deep learning models. We have three classical deep learning: CNN, we call it convolutional neural network, deep belief network, autoencoders. In our speech today, we're going to focus mainly on CNN. This is our target. We're going to use CNN, not others. So it's out of our scope, I would say. So let's focus on the CNN here. And of course, there's started with actually in 2012, the first architecture actually CNN by called AlexNet here, and it was the first DNN to win the classification. And then the structure of CNN is similar to any regular deep neural network with the trainable weights and biases weights here. Let me show now the structure of the CNN or convolutional neural network. It has many layers. It has convolution layers, the first layer, and we have pooling layers, and we have the connected layers. And of course, everyone have their own jobs here. So this is how it looks like. This is simple. This is layer 1, layer 2, 3, 4, 5. So this is the 5 layers, actually. And of course, this is the convolution layer, and this is the pooling layer. Pooling layer means down sampling or sub-sampling of the convolution layer. Now, let me explain one by one quickly. In the convolution neural network, convolution means applying a filter to a certain image. And this is what we call convolution filter. And this is here, I'm demonstrating the filter with a 3x3 filter. I have to pass across all the image 3x3, have to pass, and generate new image, which was the output actually of convolution here. And you can see it's calculating here. So this is my filter. We have to pass through the program 3x3. You have to go through by 3 and calculate the average all and overlap and scan and scan. And then by the end of the day, I down scale of the image was 5x5, become now 3x3. And it's following the convolution principle. How it looks like in the image here. This is my image, and this is my filter. I have to scan the filter through the whole image to get the output. So this is the output of the filter actually, right? Of course, depending on the filter, right? This is another output. This is the filtering here, another output. So this is the convolution, what's happening, or the output after the filtering, after the convolution. This is the first layer, actually, the convolution layer. Then we have to go to pooling layer. Pooling layer means, I say, down sampling. And then pooling layer, we may have maximum or minimum or average. Means that if I have this image here, if I use maximum pooling, that means you have to take the maximum values. So we have values 12, 20, 8, 12. Means what's the maximum value? 20. Yeah, take a 20 here. And then the second here, 30, 0, 0, 2. Maximum is 30 here. Next one, 34, 70, 112, 100. The maximum is 112. So this one maximum. If we take average, that means we have to calculate or add all these, divide by 4. Let me go for the first one. 12 plus 20 plus 12 plus 8 divided by 4, I will get 13. Maybe this one simple. 30 plus 2, 32 divided by 4, because we have 4 component average. So 32 divided by 4 will be 8, and carry on. So this is the pooling layer, and the objective of the pooling layer is to downscale or downsample the outcome of the filtering, right? Then the next one is the connect or fully connected layer. So this the last one will give us a result. This is the output layer. So we have to be fully connected. During the training, we have to use the activation function. Of course, there are so many types of activation function, right? This is the type of the activation usually used in the training. And this is the whole system together now, the development. We have the input image here, right? We have to go convolution layer. This is the output of the convolution, which is the feature map here. Then we have to go to the activation function, or what we call non-linearity. This is activation rectified linear unit. We use it here. And then we have to go to downsampling, spected pooling, downsampling. It was like this. So downsampling. And we have to go to, this is the downsampling how it works. And then we have to go to normalization. And feature map will be the output. Let me show you a simple architecture of the CNN. As you can see here, many layers here. And we see that it starts from the input, with the input layer, convolution 1, convolution 2, and some of them also pooling until they fully connect layer and the output layer. And this is how it looks like here, harmony. Right. Now, let me apply the architecture I designed now, or I showed now, to the application of the object recognition. So here I'm using some very famous Cypher 10 dataset. It consists of 60,000 images, color images. The size of image is 32 by 32 and divided into 10 classes. Means that here 10 objectives, 10 different objectives, 10 different objectives. And of course, with 6,000 images per class, and going to be 50,000 training and 10,000 testing. So the total will be 60,000. And of course, going to be randomly choose and process image from the data set here. And this is the layers. We're going to have visual layer. You see here, sampling layer or pooling layer. And this is the classes here, or the types of the images here. When you apply the convolution neural network CNN for object recognition, as you can see here, this is just video, and you can see here it's recognizing, you see, if in the traffic light, if in the car, and then some other car, and signage, you can see signage, maybe human, maybe pedestrian, you can see here. It's recognized, identifying here where the vision or the robotic vision can identify a certain objects here. And this is just for fixed image, also for object recognition, where can be identify a person or handbag or suitcase, or yeah, different objects here using a system called Euro 4 here. And this is the database I told you about, the Cypher 10 database. And this is the models CNN. Of course, there are so many models, as I told you. The first one, actually, Alex network was 2012. And of course, there are so many nowadays. Even Google network 2015, and we have even 17 also. There is updated on that. And this is the CNN models here, AlexNet, the oldest one, GoogleNet, VGCNet, ResNet, and others. And as I told you, if we apply the Cypher 10 and using different architecture here, so this is the database, and we have 10 classes here, and this is the models, CNN models, different models here. some of them VGG, RESTnet 50 layers, RESTnet 100 layers, and so on, and start here. So the accuracy actually around all of them above 90, and some of them 94. So this is the accuracy where the system able to identify and recognize objects. And this is the CNN architecture, like GoogleNet here. It has 22 layers with no what we call fully connected layers. This one, RESTnet, it has 152 layers. VGG 16 layers, and so on. So this is the architecture. How many layers inside, and how many convolution layers? Just to show some examples of how it looks like actually. If we compare the accuracy of the CNN for object recognition, and you can see the AlexNet here, the first one, it was introduced in 2012, and the latest one here, I think 17 or 18. This one, Inception 4, V4, is extension of the GoogleNet there. It's extension of GoogleNet here. This is the accuracy, and this is in terms of the operations also. You can see the Inception 4 quite the best now, because this is the extension of the Google architecture or GoogleNet architecture. See, this is the Google here, start here, and of course there is also Facebook and others. In terms of time and power consumption, this is the architectures already there, and this is about the consumption, power consumption. This is the output if we apply the CNN to face detection only. You can see here it recognizes the face almost 100%. Face has been recognized, and this is a real time for object detection for autonomous vehicles. Here you can see it's recognizing cars, signage, and others. But still, this is another one where only for pedestrians application tracking. Pedestrians tracking, you can track only the pedestrians, people moving here, only identifying. And this is especially for moving cars. Or self-driving cars also can be used. And this all can be applied for robot actually. Okay, let me, after all this short journey, let me highlight a few open issues. Means that it's like, you know, it's still a problem to be solved actually for future work for those who are doing research actually. And now machine learning models and algorithms were motivated by computer vision and image processing application. However, computer vision and multimedia do not have close interaction with neural network in the past 5 to 15 years. We expect fast development of the deep learning driven by application. Means to say that still until today, there is no standard architecture for deep learning. Every application, they have their own architecture. Maybe in the future, we're going to have standard architecture depending on the application. Also, designing and training deep models does require a lot of empirical experience. And there are also a lot of tricks and guidance provided by deep learning research. Most of them make sense intentionally, but without strict proof. So the performance of deep learning keep increasing with the size of the data. Nowadays, we're talking about the big data. So we don't see its limit yet. So still under research really. And shall we spend more effort on data annotation or model design? Explore deep learning in new application will inspire many new deep learning. Now we talk about only like image detection or recognition. I think deep learning can be used almost on all applications actually. A quantitative analysis on how to design network architecture, structures, and how to choose nonlinear operations also, like we say, of different layers in order to achieve feature invariance. Actually, I'm working on deep learning now, the framework for not only object recognition, but we try to recognize the human action. now we are I'm working in a big project about smart city. I'm taking the part of the citizen monitoring in the street here, and we need to automate the computer to identify the action of the human, like this guy drinking, or somebody running, or sitting, or fighting, or slapping, or even wrong barking. If you do wrong barking, you want to be identified and want to be warned immediately, or a theft, or slash theft, or pocket, whatever. I think let me end here with the conclusion. Deep learning has shown promise in significant sensing, cognition, and solving problems, and even the potential combine these normally separate functions into a single system. Some remaining barriers to the adoption of the deep learning and robotics include the necessity for large training data and long training times. Generating training data on physical systems can be relatively time-consuming and expensive. Ultimately, the trends are moving toward a greater level of cognition, and some researchers even believe that deep learning may achieve human-level ability in the near future. You see here, may achieve human-level ability in the near future. So currently, deep neural network appears to be a powerful tool for a practitioner in the robotics, but only time will tell whether they can really deliver the capability that are needed for adaptation of general environment. I think that's it. Thank you very much. I'm willing to respond to your questions and answer. Maybe through the live Facebook, or maybe through email. And also I'm willing to listen to your feedback. Thank you very much. Wassalamu alaikum wa rahmatullahi ta'ala wa barakatuh.